200,000 tons is the annual volume of aquatic production reached by a land once dismissed as entirely hopeless for any form of agriculture. Why did a territory thousands of kilometers from the nearest coastline, deep within the heart of inland China, become a hub for fish and shrimp farming? At first glance, the geography suggests an impossibility, yet the saline soil of the Xinjiang region has undergone a radical transformation. This area, historically labeled the Dead Sea of Central Asia, was for decades synonymous only with shifting sand, relentless wind, and salt-crusted earth. Today, it hosts a thriving industry that many now describe as an artificial ocean in the desert. The process is only gaining momentum. One can notice how the landscape of the Taklamakan Desert defies the traditional requirements for life. Covering approximately 337,000 square kilometers, this expanse is nearly equivalent in size to the American state of Texas. It ranks as the second largest sandy desert on the planet, characterized by environmental extremes that push the boundaries of biological endurance. Daytime temperatures frequently exceed 50 degrees Celsius, while the onset of night brings a sharp plunge toward the freezing point. Average annual rainfall consistently remains under 100 millimeters, and in several specific zones, not a single drop of precipitation is recorded for years at a time. The ground itself is not merely arid, but is highly alkaline and saturated with salt, leaving the surface extremely poor in essential nutrients. Strong winds move across the horizon ceaselessly, shifting the massive sand dunes and ensuring the landscape remains in a state of constant fluid change. It gets more complex further on. In the local Uyghur language, the name of this desert carries a grim warning, often interpreted to mean that once a person enters, it is nearly impossible to find a way out. This description remains a physical reality for those attempting to navigate its interior. Throughout the majority of the 20th century, the global scientific community regarded this entire region as agriculturally dead. The equipment now operating in these zones must withstand the corrosive effects of the saline environment and the abrasive nature of the wind-blown sand. One can notice the specialized infrastructure designed to harness what little resources exist in this harsh terrain. The conversion of saline-alkali land into functional ponds requires precise geological management to prevent the water from simply vanishing into the parched earth. It seems simple to pump water, but in reality, maintaining the chemical balance of these artificial basins is a constant technical challenge. The transformation marks a definitive shift in how the boundaries of the desert are perceived by modern engineering. The material is ready to move to the next processing phase without haste. 300,000 square kilometers of shifting sands and extreme temperatures define the Taklamakan Desert, a landscape where any form of life seems impossible. Why would anyone attempt to establish massive aquaculture ponds in a territory synonymous with total aridity? At first glance, the idea of raising marine species in a landlocked wasteland appears to be a violation of every fundamental ecological principle. Yet, it was precisely within this inhospitable environment that an unprecedented decision was made to cultivate saltwater fish and shrimp thousands of kilometers away from any coastline. When the initial reports regarding the plan to farm marine life in the heart of Xinjiang were made public, the primary reaction from the global community was one of deep skepticism rather than intrigue. Numerous experts argued that the desert could never serve as anything more than a barren void, incapable of supporting complex aquatic systems. Chinese scientists chose to bypass these dismissive judgments, opting instead to conduct a rigorous re-examination of the region's hidden natural structure. Detailed geological surveys eventually revealed a startling reality beneath the scorching surface. Layers of saline and alkaline groundwater sit deep under the sand, possessing chemical salinity levels that closely mirror those found in the world's oceans. One can notice how researchers identified a unique opportunity by analyzing these hidden water reserves. By carefully stabilizing this underground brine with fresh meltwater flowing from the Tian Shan Mountains, they realized they could recreate an artificial marine environment. But this is just the beginning. In the year 2022, the first experimental aquaculture ponds were officially established amidst the dunes. Each of these massive reservoirs covers an expanse ranging from several thousand to more than 10,000 square meters in total area. The equipment gradually transforms the landscape as heavy liners and impermeable membranes are installed to prevent the precious liquid from vanishing into the thirsty sand. Pumping systems and mechanical aerators operate continuously to maintain oxygen levels within the saline pools. Hundreds of thousands of juvenile fish and shrimp were released into these high-tech enclosures during the initial phase. It was a high-risk technical experiment where even a single error in salinity or pH balance could have resulted in the total collapse of the biological system. The process is only gaining momentum. Throughout these critical early stages, the teams involved made no effort to convince the world through verbal arguments or grand promises. No public statements were issued to counter the lingering doubts of the international scientific community. Instead, the project relied on the silent accumulation of data and the physical survival of the species. It is visible how the water remains clear as biological filtration systems scrub impurities from the artificial seawater. Eventually, the raw results and the health of the thriving schools of fish provided the definitive answer to the skeptics. The material success of the harvest proved that the desert could indeed host a productive marine ecosystem through precise engineering and geological utilization. The transformation of the environment concludes this phase, opening the road to a new era of inland resource management. 99% is the unprecedented survival rate achieved by fish within the aquaculture ponds established deep inside the Taklamakan Desert. Why is such a high percentage considered a breakthrough in the global fishing industry? While high-yield environments are common in laboratory settings, maintaining such stability in a desert wasteland contradicts traditional biological expectations. Even in leading maritime nations like Norway, where coastal salmon farming has been refined through decades of technical optimization, typical survival rates generally fluctuate between 60 and 80%, depending on local disease outbreaks and shifting environmental conditions. The desert systems demonstrate a superior level of biological resilience. Juvenile fish introduced into these artificial basins grew steadily over the course of several months until they reached full market size. This rapid development proves that a tightly controlled artificial environment does not merely allow aquatic life to persist, but actively supports highly efficient industrial growth. It only looks obvious that fish require water to survive, but in reality, the Taklamakan transitioned from a barren void into a massive living experiment. But this is just the beginning. China utilized this site to transform concepts once dismissed as absurd into a measurable physical reality. The success forces a global reconsideration of the geographical limits governing modern aquaculture. One can notice how the results achieved in these sands were never a matter of chance or luck. Every variable within the desert production chain is calculated with mathematical precision. Unlike conventional fish ponds that rely on natural water exchange, these desert units function as closed biological systems. They are lined with thick, impermeable membranes that create a total physical barrier, isolating the water from the corrosive saline soil located directly beneath the basins. Pumping mechanisms, aeration devices, and biological filtration arrays operate continuously 24 hours a day and 7 days a week. One can notice the equipment gradually maintaining oxygen levels, salinity, and water temperature in a state of constant equilibrium. At first glance, the climate seems insurmountable, but the system remains unaffected. In an environment where daytime temperatures frequently exceed 50 degrees Celsius and then drop sharply after sunset, the pond water remains stabilized between 20 and 30 degrees Celsius. Automated regulation systems and thermal sensors react instantly to any external atmospheric shifts. The process is only gaining momentum. More importantly, over 90% of the total water volume is recycled through a complex internal loop. Waste products and uneaten feed particles are directed through settling tanks and specialized biological filters, where they are neutralized before the purified water is returned to the main ponds. In a desert landscape where water is more precious than any other physical resource, this circular mechanism represents far more than a simple technical solution. The water moves through the filters with a rhythmic flow, ensuring that not a single gallon is wasted in the production of high-quality protein. $5 billion is the staggering total investment required to sustain the high-tech aquaculture model within the arid landscapes of Xinjiang. This massive financial influx represents over a decade of meticulous preparation and technical implementation aimed at transforming the desert. Why has the capital requirement surged so dramatically in recent times? one can notice that approximately $1.6 billion were concentrated into the project during just the last 24 months. This coincided with the transition from experimental phases into a fully realized commercialization stage, where the systems must operate at peak industrial capacity. The process is only gaining momentum. High initial expenditures are being systematically balanced by significant economic yields as the infrastructure matures. During 2023, the total aquaculture output across Xinjiang reached approximately 184,000 tons. This production volume generated a revenue exceeding $530 million for the region. By 2024, the output climbed further to nearly 196,500 tons, cementing the territory as the primary aquaculture hub in northwest China. It only looks obvious to see these figures as simple profits, but in reality, they represent the total reclamation of land previously categorized as worthless. The Taklamakan Desert is witnessing the birth of a food production industry with an operational efficiency that matches the advanced aquaculture standards found in Norway. But this is just the beginning. Precision control over water chemistry, thermal stability, and salinity levels has allowed the project to evolve beyond the basic rearing of aquatic life. It is visible how the ponds have gradually begun to function as an integrated artificial ecosystem. Within this framework, biological links and mechanical systems work in tandem to sustain a stable environment over long durations. The story does not end at this stage. Microorganisms within the settling tanks and specialized biological filtration units have started performing ecological roles typically reserved for the open ocean. These microscopic entities break down organic waste and neutralize toxic chemical compounds to ensure the water remains habitable. According to the technical project descriptions, over 500 distinct species of microorganisms can thrive within this closed loop. Everything only gets more complicated as these organisms produce natural nutrients, which significantly reduces the operational dependence on expensive industrial feed. One can notice that these structures are no longer merely industrial fish ponds, but have transitioned into complex living systems. 90% of the water utilized in this desert aquaculture system is cycled back into production through a specialized closed-loop technical model. Why is such a high rate of recovery necessary for the facility? The resource scarcity of the Taklamakan Desert demands that every gallon be preserved. It is visible how the nutrient-rich liquid, once filtered from the fish tanks, transitions from the pond's edge toward a different industrial application. Instead of being discarded as waste, this treated water serves as the primary irrigation source for agricultural experiments on surrounding saline-alkaline land. But this is just the beginning. The equipment gradually redirects this nitrogen-heavy outflow to support the cultivation of salt-tolerant rice varieties, a crop specifically engineered for environments once considered impossible to stabilize. Since the year 2018, these trials in Xinjiang have targeted soil where salinity levels frequently exceed 1.7%. At such high concentrations, conventional cereal crops would perish within days due to osmotic stress. At first glance, the soil appears completely barren, but in reality, the combination of specific genetics and recycled aquaculture water allows the plants to thrive. The process is only gaining momentum. One can notice how the rice stalks maintain their structure even in these harsh chemical conditions. By the year 2023, the total area dedicated to this sea rice in Xinjiang expanded to approximately 2,000 hectares of land. The technical data reveals that yields have reached over 8 tons per hectare. This volume is significant because it matches the output of many traditional non-saline rice-growing regions. It gets more complex further on. The system relies on a stacking mechanism where each industrial layer supports the next. One can observe the fish farming units providing a constant stream of organic nutrients and moisture. Simultaneously, the rice cultivation stage works to improve the storage capacity and structural integrity of the desert soil. The camera glides along the perimeter where the transformation of the landscape becomes evident through these integrated cycles. Everything only gets more complicated as the scale of the experiment grows. These two distinct systems function as a singular biological engine, turning waste into a resource for the next phase of production. The material continues its movement through the desert infrastructure, proving that the technical limits of the environment can be bypassed through calculated recycling. Thus, the integrated production cycle concludes its current phase, leaving the soil ready for the next seasonal transition.